Okay, welcome back everybody. Math 131, Lecture 10. We are moving along. As I promised yesterday, we're going to come back and work another problem, curve sketching using derivatives. So we'll get another little taste for it. And then I like to jump right now, even in my own campus classes, to Chapter 3, Section 1, another rule for the derivatives, and it's product and quotient, because sometimes working the optimization problems, a product rule seems to make the arithmetic a little easier, or the calculations a little easier. So we're going to jump and do 3.1, and then we're going to come back to the optimization. I've got a better copy of the supplement for the optimization problems now posted. Actually, your wonderful TA retyped every one of them and put it there for us, so it should stay there forever. So if you'll look at the computer screen, Math 131 supplementary optimization problems. What I like about my set is that I have it grouped for you so that you can just work on one type at a time, and the answers of course are here. 1 through 5 are your geometric applications, and that will be one type you're responsible for. The first one is a rectangle. The second one is a box without a top. The third one is a square base rectangular box without a top. And the fourth one is a box again. And the fifth one is a little right circular cylinder, a cylindrical coffee can. Okay? And those approximations mean that when you solve for R or H, you just plug it in your calculator and get a good approximation. You will want to work through these for extra practice, as well as the textbook questions. Okay, problems 6 and 7. Problems 6 and 7. These are what we call some business and economic applications. This one is the type where you want to know, if I go up on the price, I'm going to lose a little business, but should I go up on the price of a ticket and take less people coming in and still come out ahead more? Or in problem number 6, it applies to like apple trees in an orchard, because if you overcrowd your trees on a plot of land, then they don't get the nutrients they need, and so you decrease the apples on the tree. Or you have a restaurant. You know, how many people should you sit in your restaurant so that you maximize your profit? Well, you could crowd everybody in there elbow to elbow, bumping into each other. But every time you keep adding more people and it gets more crowded, then you're going to get people who are going to quit coming. So you're looking for what's the optimal amount, number of people, so that you maximize your profit. So the number 6 is just showing you how you could do it with trees. Number 7, a lot of these numbers were picked because problems were picked with numbers that aren't too realistic, just so the numbers are not too bad. But that's like trying to decide the price on tickets for a basketball game, because every time the prices go up, you start to lose a few people. They're well past $6 a ticket now. What are they? 50? Okay. Well, they're worth it. Okay. Then the last two problems, number 8 and 9, are what we call inventory costs. You're running a business, and you know about how many items you're going to sell at a time, in a year. So do you order them all at the beginning, or do you order them spaced out? And if so, how many times a year do you order, and what size do you order? And those are called inventory. And actually the inventory shows up in section 2.6, I think. So for this particular book, 8 and 9 show up in section 2.6. I think the problems 6 and 7 show up in 2.7. It says 2.6, but I think in this particular edition, this is an old supplement. And then the first one, of course, shows up in 2.5. Okay, it's a great supplement, kind of organized to give you the drill to do whatever you need to do to master it. Okay, so we want to start out today with some curve sketching again to revisit that. And I picked a different problem for us to do that we haven't done one like. And also there's one little thing here I want to teach you about. And we want to use derivatives to sketch the graph of y equals the cube root of x. Y equals the cube root of x. Okay. Use our derivatives to help us sketch this. All right, so let's go ahead and set up our coordinate system. Remember, you want to make your graphs very obvious. Is it concave up, down, increasing, decreasing? Spread out those units. And of course, I know we could sketch this by plotting points, but that's not the instructions to the problem. Okay, I don't know where we are on the y-axis yet till we start with some problems, some numbers, get some information. Okay? Alrighty, what's the first thing in my little easy cookbook directions? What do we look at? Okay, we're going to look at the domain, any intercepts that we can find. The y is always easy. Sometimes the x is easy. Any asymptotes we might have, anything unusual. All right, so we'll do it like we did yesterday. So what is my domain here? We're looking at a cube root of x. Okay, square root, we can't take the square root of a negative number. An even root, we can't take. But what about an odd? What's the cube root of 8? 2. What's the, why? Because 2 times 2 times 2 is 8. What's the cube root of negative 8? What can you multiply times itself 3 times to give you negative 8? Negative 2. So you can take an odd root of a negative number, right? It's just an even root you can't take of a negative number under the set of real numbers. So I can take the cube root of 0, I can take the cube root of a negative number, I can take the cube root of a positive number. So my domain is x is the element of the reals. It's going to be all real numbers. Close that off. Okay? All right, so I'm expecting my graph to cover all real numbers when I'm done. All right, do we have any intercepts? Yeah, when x is 0, y is 0, so we know the point 0, 0 is on the graph for sure. When x is 0, y is 0, and so you can only have one y-intercept, and that happens to be your x-intercept. So let's put our zeros right here. Okay? All right. This graph, does it have an asymptote? You're looking at your asymptotes as x gets really big. You're kind of taking the limit of this. As x gets really, really big, what happens to y? You're looking at the limit. What's the limit of that?
Infinity.
Infinity. So it doesn't have a horizontal asymptote, or as x gets really small, it heads to negative infinity. And there's no division by 0 that would make a vertical asymptote show up. So there are none. So there are no asymptotes. Okay? All right. So what's the second thing we're going to look for now? Derivative. Because now we want to know about increasing and decreasing. So I'll just write like f of x is equal to x to what power?
1/3.
1/3. All right. So now let's take the derivative. What is it? Okay, 1/3 x to the negative 2/3. All right, let's write that without a negative exponent. The negative 2/3 means carry it down to the denominator, so you got a 3x to the 2/3 power, and it might be easier to think about if you say 3 cube roots of x squared. Can you see that? You can. 1/3 cube roots of x squared. All right, now what are we supposed to do with this derivative? Set it equal to 0. Somebody give me some thoughts here. Can this fraction ever equal 0? No, the only way you get a fraction to be 0 is when the numerator is 0. Okay, so that just kind of messed up our rule, didn't it? Our possible extreme points, we've seen they've occurred where we had horizontal tangent lines. All right, now I want to tell you one more new thing. All right. Suppose we had a graph like this. I mean, that's a perfectly great function, right? I mean, that's a function, right? It passes the vertical line test. It's a function. All right. But what do you know about with respect to the derivative at this point right here? Does the derivative exist at this point? No, it's one of those sharp point deals where the tangent line coming off this way is here, the tangent line coming off this way is here, so the derivative does not exist at that point. Okay, so here there was no way the derivative could be equal to 0. It's never equal to 0. So now let's say, is there a value for x in the domain of the function? The domain of our function where the derivative does not exist. Okay, so we looked at right away the the function was defined for all values of x. I take the derivative and set it equal to 0, and there's no way my derivative can be equal to 0. So then I ask myself, because we all understand about derivatives not existing at a sharp point, corner, vertical tangent kind of deal, well, is there a value for x that is in the domain of my function, because I'm looking for a point on the curve, so I had to go to my original function. Is there a place where this derivative does not exist? So what makes this expression, which is the derivative, not exist? 0. When x is 0, we have 1 divided by 0 does not exist. Okay, so new rule to add to your mini rules. We have a possible extreme point where the first derivative equals 0, or where the first derivative does not exist. Okay, but where it does not exist, that value has to be in the domain, because otherwise you don't have a point there. Got it? All right. So you're telling me to check out where x is 0, because that's where it doesn't exist. So let's do our little sign chart around 0. Okay, I'm using my derivative. To determine, is it increasing or decreasing around where x is undefined in the derivative, where the derivative doesn't exist. All right, so if I pick a number bigger than 0, what do we know about the first derivative? A number bigger than 0? Positive, right? So the first derivative is positive, which means what on my graph? Increasing. So let me just go ahead and draw that little increasing. So as long as I'm bigger than 0, the curve is increasing. All right, I'm just doing a slight sketch. If I were doing this on my own paper, I'd use pencil to show increasing. Okay? All right, now let's pick a number less than 0, such as -10. If I put -10 in this expression, is it going to be positive or negative? It's positive, because I'm going to square that -10, then I'm taking the cube root of a positive number. So I have a first derivative greater than 0, so it's increasing when x is less than 0. So for x less than 0, it's still increasing. Okay, so have I found an extreme point? No, I used my first derivative. It goes from increasing to increasing. If I were going to have an extreme point, it might be where the derivative does not exist, but in this case there are no extreme points. Okay, so no extreme points. And there's no extreme points because we used the first derivative test and it went from increasing to increasing. Okay, if there was an extreme point, it would have been at x equal to 0. Okay? All right, what's the next thing we're going to do? All right, they just told me if it went up or down. Now what are we going to do? We're going to put some shape to the graph. Exactly. All right, so remember, first derivative just tells me if it goes up or down or straight across for a horizontal tangent line. All right, part 3 is going to put my shape. Okay, so we're going to go to the second derivative. Second derivative, let me write up the first derivative so we can look at it. 1/3 x to the negative 2/3, 1/3 x to the negative 2/3. Okay? All right, so the second derivative is going to be what? Negative 2/9 x to the negative 5/3. Subtract 3/3 from negative 2/3 and you get negative 5/3. All right, so let's put this in here. We get negative 2/9 cube roots of x to the 5th. Now, if you want to put in every step, you got minus 2/9 x to the 5/3, and that becomes negative 2/9 cube roots of x to the 5th. Okay? All right. Now, what do we do with this second derivative? We're going to set it equal to 0 for what? Possible what? Inflection. What's the definition of an inflection point? Where the concavity changes. All right. For what value of x makes this second derivative equal to 0? Nowhere, right? The only way you get a fraction to be 0 is when the numerator is 0. So we have new extended rule. New rule. Possible inflection point where, of course this point's got to be in the domain of the original function, right? Point where second derivative equals 0 or the second derivative is undefined. Second derivative is undefined. Okay? And that means that you got a division by 0 or something. Okay, but you got to be in your original function. All right, so this is, there's nowhere that makes it equal to 0. So the place where it's undefined is going to be again at x equal to 0. So let's set up a little sign chart. All right, if I put a 10 in for x, all I want to know, is this expression going to be positive or negative? Negative, right? If I put a 10 in, the denominator is positive, the numerator is negative. So my second derivative is less than 0, which means what? Concave down. Okay, so I'm going to go to my graph. When x is bigger than 0, I'm going to trace over this line and make a concave down. The derivative gives shape to the graph. Concave down, increasing. Okay, everybody see that? All right. Now let's go when x is less than 0. You might wonder why I didn't do the negative first. You know there are these people that start at the back of a magazine and go to the front? Okay, well that's me. So I guess I start on the positives and head to the negatives, and a lot of people would start on the negatives and head to the positives. So if I seem a little, I don't know how your personality is, but I always start at the back of the newspaper, magazine. So I start at the back of the magazine and go towards the front. I don't know why. So a lot of people would have started here with negatives and then gone to positives. So if this is bothering you, just know it's okay. There are other people like me. All right? Okay. x less than 0, such as negative 10. What's going to happen if you put a negative 10 and raise it to the 5th? You get a negative number, and the cube root of a negative number is a negative number, and so you got a negative over a negative, which is a positive. So we have a second derivative greater than 0, which means concave up. Concave up. All right. So, excuse me? Yes, thank you. At x equal to 0, which also had y equal to 0, we have an inflection point. Yes. Because the concavity changed around it. Thank you very much. Very good. All right, so now let's finish sketching our graph. It's going to be concave up when x is less than 0. So it's increasing concave up. So we'll just curve it around like this. And there is a good sketch. And in fact, I did almost a good job, because when x is 1, y is 1. And when x is negative 1, this little number right here is out of place. When x is negative 1, y is negative 1. So there are some graphs there. Okay, the main thing was you saw it was increasing. This is concave down. This is increasing, but this part is concave up. Pretty good, huh? Isn't that neat? Don't you love using the derivative? Yes. I didn't hear you. Yes. All righty. Work on those and get good, good, good. All right. As I told you, I'm jumping to Chapter 3, Section 1, because I want to give you some rules. Rules for derivatives. And, of course, this is product and quotient rule. Okay, these are a must. These are a must. What are you doing? All right. So far, if you had to take the derivative of something like y equals x squared times x minus 3, if you had to take the derivative of this, where it's not a constant times a function, but a variable or a function times a function, what did we need to do before we could take the derivative? What did we do? You had to simplify it, multiply it out. You got x cubed minus 3x squared. And then you took the derivative and got 3x squared minus 6x, correct? All right. Well, that's not too bad, as long as this is not like a x minus 3 to the 10th. Because if it were like a x minus 3 to the 10th, you'd have to multiply that out 10 times and then multiply it times x squared and do term by term. Okay? All right, so we have a rule, a product rule. Product rule is saying when we have two functions, f of x and g of x, two functions of x multiplied together. By the way, we can use the product rule if it's a constant also, because x equal to 3, 3 is a function. And remind me to come back and do that. But basically we're thinking about right this second, f of x times g of x, two functions multiplied together. Now remember, this was when you had them added or subtracted. You could do one term at a time and take the derivative. But the rule was not for multiplication. All right, so I'm going to flip in the book to section 3.1 and show you the rule. And then I'm just going to tell you the words I used, and we're just going to say it over and over and over till it's very easy for us. Product rule. Bottom of page 215. Bottom of page 215. Can you see that? All right. Looks pretty ugly till you put the words to it, and then it'll be easier. It says that when I'm taking the derivative of two functions multiplied together, f of x and g of x, two functions multiplied together, it's going to be equal to the first function times the derivative of the second function plus the second function times the derivative of the first function. Okay? Now, everybody has little ways they remember things. So for me, I just go first times the derivative second. plus second times derivative first. First times derivative second plus second times derivative first. Anybody have any way you learned it from somebody else that had any little words to say? Okay, will you people be happy with first and seconds? All right, let's mumble together. If you have two functions multiplied together, the derivative is
First.
times plus. Okay, without looking down at your paper or up here at my work, turn to your neighbor and tell them what the derivative of two functions multiplied together.
First times second plus. Yeah.
How'd your neighbor do?
Excellent.
Excellent. Okay. All right. So let's apply it right here. dy dx. All right. Now you could write out f of x, derivative of f of x, g of x, derivative of g of x, but somehow I believe we can do part of this mentally. All right. So the rule is, this is my first and this is my second. So the rule is what? First, just like you see it, times derivative of the second. What's derivative of the second? 1. Plus, okay, first times derivative of second, plus second times derivative of the first, which is,
2x.
oops, I was running out of space and I got myself all confused. That's a 2x. Can you see it? Okay. I had to write on the back of that page.
Does it say plus 2x?
All right, first times derivative of second plus second times derivative of the first. Okay? All right, so let's just clean that up and see what we have here. X squared plus 2x times x is 2x squared minus 6x, which is 3x squared minus 6. Bingo. 6x. Thank you. Thank you, thank you, thank you. All right. So the product rule is when I have two functions multiplied together is first, just like you see it, times the derivative of second plus second times the derivative of first. All right, mumble it again.
First times derivative of second plus second times derivative of first.
Okay, here's the example. I want you doing it first on your own, then check your neighbor's work. Find the derivative. Do you want to go for hard or y'all need another easy? Go for hard. I love it when you beg for hard problems. You are begging. All right, you don't have to simplify this because it'll probably be a mess. I'm going to give you the hardest I can think of, and let's see how you do. All right. Find the derivative. That's about as hard as I can think of. Don't forget proper notation. Don't forget your proper notation. You got it? Right. Wait a minute. Yeah. Because you're using your general power rule. Yes, very good. Very good. First times the root of the second. Is that your general power rule? Did you forget something real important there? You brought it down, rewrote, decreased by 1. And then what else for the general power rule? which is yes. Yes. Very good. Mark that so you don't forget on the test. If you make a little mistake, you really want to highlight it so you don't miss it on the test. And I see everybody making the same mistake. Let me see if I can find somebody who got it right. Oh, yeah. Good job. Yes. Okay, I'm still seeing everybody making the same mistake. Let me see what you did. Right, you had to use your... All right, so I had a general power rule inside of the product rule, right? A couple of times. But it's not a problem to you because you're following the rules and you know your rules. All right, so we have 7x cubed plus 1 to the 10th times 5 minus x to the 1/2. All right, let's do it together. The rule is what is the first part of the rule? First. So it's the first just like you see it. All right, let's just go ahead and feel good. How many got that much right? Oh, yeah. All right, now, times derivative of the second. So I'm going to take the derivative of 5 minus x to the 1/2. What rule am I using here? General power rule. Bring the 1/2 down. How do you rewrite it? Rewrite exactly. Decrease by 1. And what did the rest of you leave out? The derivative of the inside, which is -1. The derivative of 5 is 0. The derivative of minus 1x is minus 1. Okay, here comes the red pens. Mark them, mark them. Send these around. That -1 gets missed a lot. Okay? All right. Watch that. That does get missed. 5 minus x, its derivative is minus 1. Okay, so it's first times the derivative of the second. That's a good little general power rule. Now what's the rest of this? Plus the second function, just like you see it, times the derivative of the first. What rule are you using? General power rule. Bring the 10 down. Rewrite, what's the word? Exactly. Decrease by 1. And do you stop there?
No.
What's the inside? 21x squared. Okay, 21x squared. All right, I didn't want you to simplify this one. This was kind of an ugly one. This is the place right here where mistakes are made. Okay? All right, let me let you redeem yourself and everybody get it right. How many got it all right except for that -1? Okay. What'd you do? You missed a square right here? Oh, forgot to do it. Yeah, you almost have to listen to yourself say exactly what you're doing, because if you ever get on automatic, you miss a lot of things. So you wanted to hear yourself say the derivative of 7x cubed is, bring the 3 down, 3 times 7, 21x, decreased by 1 squared. You have to listen to yourself. All right. Anybody want to help me make it up?
You're doing just fine.
I'm doing just fine on my own. All right, I'm going to make this.
Super hard.
Well, that one was pretty hard. Let me see if I can think of something else. 5x to the 3x to the 5th. I already had 5 in my mind. Times. Okay. X to the 8th minus. Okay, this is going to be really hard. 1 over 2x raised to the I don't know. 4th? Okay. To the first. No, that'd be too easy. All right, go for it. Get it right, everybody. Did the red pens make it to the back? You guys sending? Here's the red pens. Keep sending them around. You are good, good, good. From Orangeburg. You are very good. Are you very good too? Recheck that.
Yeah, simplify this.
No, don't simplify it. I'm just giving you hard stuff. The problems in the book are much easier. I'm giving you more than your money's worth. Of course, this is the kind of problems I put on test, right? Okay, if you are missing this problem, it's because you are missing what you learned for the first test, and that is how you're going to take the derivative of 1 over 2x. So let's rewrite that. 3x to the 5th times x to the 8th minus. How are you going to deal with this 1 over 2x? Okay, several ways. You could write it as 1/2 x to the negative 1. That's probably the easiest way to do it. If you carried the 2x up to the numerator, it would be the whole thing to the negative 1 power. It would be parentheses 2x to the negative 1 if you carried the whole thing up. All right, and we'll raise it to the 4th. So this is what you're telling me you did. You wrote it as x to the 8th minus 2x to the negative 1 to the 4th. Okay, that's fine. Just remember when you do your general power rule there, you got to remember to take the derivative of the inside. That would be okay. Alrighty, so this part right here is where I was concerned that the mistake was going to be, and that's not even the new content, which is product rule. Okay? All right, how's your notation, everybody? Derivative equals. All right, how do I know I'm going to use a product rule here? How do I know? Two different functions are multiplied together. Okay, so I know I need a product rule. All right, so we have the first times the derivative of the second. Bring the 4 down. Rewrite exactly. Decrease by 1. Derivative of the inside, which is
7 plus 2x.
okay. I brought the negative 1 down in front, made that positive 1/2 x, decrease that by 1. All right, so that's the first times the derivative of the second plus second function. Now we're on easy street. Times the derivative of the first, which is just 15x to the 4th. Okay, that came around here. That's not a division line. I ran out of space. Sorry. Carried around. Okay? Let me just make sure when you took the derivative of this part, you brought the 4 down, rewrote exactly, decreased by 1, and then the derivative of the inside, you got 8x to the 7th, and then what was this part?
I did. Minus 2 raised to the negative second.
You got to bring the negative 1 down in front, which makes that plus 2x to the negative 2. What else? Derivative of that inside. So you'd have to put a 2 there. Okay. I was just looking at that little part right there in case you rewrote it this way. So you brought your negative 1 down, rewrite exactly, decrease by 1, derivative of the inside. Okay? All righty. Last little question, and then we're going to the quotient rule. I mentioned that you can always use a product rule even if you had a constant times a function. Okay? I had said if you had a function times a function. Well, 4 is technically a function. It's just a straight line. All right, so we're going to pretend that you momentarily forgot that if you have a constant times a function, the derivative is the constant times the derivative of the function. So let's look at the derivative of this. Okay, so you got the first, which is 4, times the derivative of the second. Bring the 10 down, rewrite, decrease by 1, derivative of the inside. So it's first times the derivative of the second. Brought the 10 down, rewrote, decrease by 1, derivative of the inside. Plus the second function, x squared plus 3 to the 10th, times, what's the derivative of 4?
0.
0. So that makes that part 0, and that part just turns out to be your general power rule to begin with. So you can, even if there's a constant there, you can go with the product rule. Okay? Alrighty, let's go with the quotient rule. And this is going to be when you have one function divided by another function. All these, by the way, were derived by the definition, the limit definition of the derivative, and you can just thank your forefathers for figuring that out. Okay, and of course this has to be where your denominator is not equal to 0. All right, the quotient rule is on page 217, called the quotient rule. And does that ever look ugly? So we're going to see how do we use words to make this sound better. All right, I have two functions, one divided by the other, and the derivative is the denominator, g of x, times the derivative of the numerator, minus the numerator times the derivative of the denominator over the denominator squared. Now, aren't you glad somebody figured this out before your time? So you didn't have to, you could have done it, yes? Probably the people who published these didn't make money for publishing them. Okay, they just got their name in print. All righty. Anybody who's had calculus before, did you hear something? Okay, what'd you hear?
My friend told me low d high minus high d low over low squared.
Okay, this is called the yodel. You know, you've heard yodeling. All right, I'm not good at this. All right, you call the top f of x high. You call the denominator low. Okay, so low d high minus high d low over low low. Now, I don't know how to yodel, but low d high minus high d low over low. I told you I couldn't sing or paint, so don't worry. Over low low. Okay, but who sings in here? Somebody want to yodel for us? All right, I can never remember the yodeling, but without seeing what it is. So if you like low d high, derivative of the high number, minus high d low, the derivative of the low number function over the denominator squared. All right, the way I remember it is I just call them bottoms and tops because I'm sure that's the way my teacher taught me. This is the top and this is the bottom. All right, and then I do something really silly to help me visualize the formula. So we start at the bottom. All right, this is really silly. Too bad it's on tape. All right. All right, so we go. I mean, if I do it and it's silly, you'll remember it, so that's all I care about anyway. So we go bottom times the derivative of the top. And then when you turn around, doesn't that make a different direction? So we're going to have minus. So we go bottom times the derivative of the top minus, because we're turning around, top times the derivative of the bottom. And then you think of a referee over bottom squared. So all of you doing the test are going. Okay, and this is the part people forget. Over the denominator squared. So bottom times the derivative of the top, turn direction, minus top times the derivative of the bottom over bottom squared. All right. I have a lot of cute little stupid stuff that helps me remember things. So however you have to memorize it, go for it. So turn to your neighbor and tell them how you're memorizing it and do it for them. Okay. All right, so however you're doing it. Right. Okay, I'm sure I'm going to do bottoms and tops because that just works for my visual of this. All right, so let me make up a problem, one that's not too terrible for our first example. Just do what it says. 3x squared plus 1 over, not too bad, right? Okay, not too bad. 5 minus 8x. All right, I didn't need a parenthesis in the top. I was going to make it a little more interesting, but we'll do another one more interesting. So it's 3x squared plus 1 divided by 5 minus 8x. Find the derivative using the quotient rule. And feel free to mumble your rule, because the more you mumble, the better you get. Okay, check your neighbor. Check your neighbor. Got it? All right, let's do it together and see if your neighbor is correct.
Oh, I forgot my loaf.
You didn't forget the over the low square, did you?
I did. Just when it's simplified.
Okay.
I got it.
All right, I'm going to have to go with the bottoms and the tops since I can't yodel, but you just yodel to yourself if that's what you're doing. All right, so it's the bottom just like you see it. How many got that much? All righty. Times the derivative of the top, which is 6x. How many are we still good? All right, so it's bottom times the derivative of the top. Now what's going to happen? Minus. Okay, that's where mistakes are made. You're changing directions here if you're visualizing this. Bottom times the derivative of the top minus the top, just like you see it. What is the derivative of the bottom? Yes, thank you. Minus 8. And what's the next biggie? Over the bottom square. How many got the whole problem right?
Oh, except for the negative 8.
Oh, then you can't raise your hand.
I had to let her know about it.
Okay, very good, very good. Now let's make up a hard one.
So do we never have to simplify it?
That wasn't hard?
No, that one wasn't hard. The hard ones you're not going to have to simplify. In your book, you're going to need to be able to simplify, and they're usually pretty easy. That one would have been easy to simplify, actually. Because you would just multiply the 6x times each of those, and the negative x distributed. It would have just been easy to clean up. Yeah, just combining your... You can't... Oh, wait, I know I didn't hear you say this. You didn't say divide this out with this one, did you? You can't divide. If you were simplifying, you could not divide this out with this. Why? There's a minus in there. The only time you can divide out is when everything is completely factored, then that would be a b over a a. But if you had a plus b over a squared, that is not equal to 1 plus b, right? Okay. So I'm glad you wanted me to remind everybody you can't do that. All right. Okay, let's go for a really hard one. And we're not simplifying, we're just getting it out there. Anybody want to help me make it up? Okay, really, really hard. Really hard. The fifth root of what? Plus 7. All right, in the numerator, let's have 5 minus x to the 10th. All right, find the derivative. How do you know you're using a quotient rule? You got a fraction here, a function divided by a function. Okay, go for it. Check your neighbor. Actually, I need to get somebody's paper. Can I have your paper? All right. Let's see if we can see this. And all right, y equals 5 minus x raised to the 10th over the 5th root. All right, does anybody see anything incorrect yet in the first line? Can you focus in just even on that first line more? Anything wrong right here? Looks like you were trying to carry that up to the numerator or something.
No, that's irrelevant.
Oh, this is irrelevant.
Yeah.
Okay. All right. Don't confuse me.
Sorry.
Okay. Then, all right, then let's go down to this part. Anything missing here? All right, so let's get the derivative in there if you're working on it. Okay. All right, now I'm not quite as confused. All right, so now we can back out just a little bit so we can get the whole thing there. Perfect. Perfect, perfect. All right, let's double check it. That looks like the bottom times the derivative of the top. Would you say that that part is correct?
Yes.
I'd say that's perfect, perfect, perfect. Minus the top, and would you say this part is correct?
No, it's 3x squared.
3x squared.
Not 2x squared.
Oh.
Yeah, right there.
Yeah.
Would you say that's perfect?
I would now. I didn't even see it. Okay, let me get these glasses out. Yes, thank you. Yeah, you got to be really careful. Top, derivative of the bottom, brought the 1/5 down, rewrote, decreased by 1, put that to a negative 4/5. Derivative of x cubed, 3x squared, and the derivative of 7 is 0. Correct. And then what about down in the denominator? and it is squared. By the way, what is x cubed plus 7 raised to the 1/5 squared? X to the 2/5, right? Power of a power, just in case you were wanting to know that. So this is almost perfect. Almost. 2 little mistakes. Thank you. Thank you. It's better to see your work than mine. Everybody good? Okay, great. Now you're an expert in product and quotient rule. When you're working some of the optimization problems, it might be easier to use a product or quotient rule than to multiply all the algebra parts out. All right, if you open your book, we're on page 187, back into optimization, page 187. Remember, what we have to do is we have to come up with a function that we need to maximize or minimize. And then we're going to use our derivatives to help us maximize it or minimize it. Okay, we're going to look at problem number 16. We have a closed rectangular box. That means it has a top on it, closed. If it doesn't have a top, it's called open. So we have a closed rectangular box that happens to have a square base, and we know the volume of this box is 12 cubic feet. And we're going to construct it using 2 different types of materials. The top is made of metal that costs $2 per square foot, and the remainder is wood costing $1 per square foot. Find the dimensions of the box for which what? Cost of the materials is minimized. All right, that last little part there tells us what the function is that we're going to have to come up with and minimize it. We got to come up with a function for the cost of the materials for this box, and we want that cost to be as small as possible. Okay? So we know where we're headed, a cost function. All right? So let's see if we can draw the box, because I'm going to have to move the book. Everybody got the problem? Page 187. Page 187, problem number 16. Okay. Let me just draw the box and we'll keep referring to it. Closed rectangular box with a square base. So here's my square base, or somewhat like that. That might be my front. My boxes always look funny till they're not always perfect, but yours probably aren't either, are they? Let me draw it. Oops. My square base does not look exactly square, but this is my base. What I have to say is if that doesn't look like a square to you, you probably stayed out too late last night. Okay. All right, so if I have a box with a square base, let's make up some dimensions. We'll just call it a x by x. All right, it says a closed rectangular box with a square base. And so when we have a box, we definitely have a height. And the other piece of information is that it tells me that, you know, this is every square box base in the world. But my box must hold 12 cubic feet. All right. I'm going to be working for getting the materials on a box that holds exactly 12 cubic feet. All right. Now, the other little parts I want to notice is the top is made costing, the top cost $2 per, and I always write this and it seems to help everybody understand it better. It's $2 per 1 square foot. Okay, so let's just think about the cost of the top. It's $2 per 1 square foot. Let's pretend this is a 3 by 3 on the top. 3 feet by 3 feet. So how many square feet would I have in the top if it's a 3 by 3? 9. So then what would it cost me for the top? 18. Okay, so for my particular problem, when I have an x by x top, okay, what is the cost for the top of my box? Okay, the area of the top is x squared, just like the 3 times the 3, 9 times, right, 9. Okay, x squared, and so the cost will be 2 times x squared. Exactly. So the cost of the top. Cost of top. Okay? It's $2 for 1 square foot. I have x square feet. Just like if it were a 3 by 3, I would have 9 square feet. 9 times 2. I have x times x square feet times 2. Is that clear? Okay. The rest of the box is made out of wood, and it's only $1. Okay, so let's go to the bottom. It's going to be $1 per 1 square foot. So again, if this were 3 by 3, I would have how many square feet? 9. And the cost of the bottom would have been 9 times 1, right? How many square feet do I have in the bottom of mine? X square feet, and it's $1 per square foot. So the cost of the bottom for me is going to be 1 times x squared. Does that make sense? Okay, now let's look at the front face, side faces, and all this. This side face, the dimensions are x by h. This part is also a x by h. What about the front? Another x by h. And what about the back? X by h. So since I have a square base, the front, back, sides are all x by h's, right? So what's the area of the two sides and the front and back? 4xh, right? 4xh. So for all the cost for the sides and front, that's front, back faces, it's going to be 4xh. That's my area. xh plus xh plus xh plus xh. And then per square foot, it is $1. Okay, so we'll multiply that times 1. I mean, it would probably been easier if you'd seen it like $3 a square foot. It would have been 3 times the 4xh. All right, is everybody clear on where 4xh is? And why I multiplied it times 1? Because that is the cost per 1 square foot. All right, we're ready to set up our equation, because what are we going to minimize? Cost of materials to make my box. Okay, so let's write our function for cost. All right, so this is number 16 on page 187, 16 page 187. So we have to come up with our cost function. All right, so the cost of the top, you told me, is 2x squared. Okay, the cost of the bottom is 1x squared. All right, I'm just going to write x squared. Everybody okay with that? It's 1x squared. And the cost of the two sides, the front and back face, is 4xh. Okay? So I have a cost function, but guess what? This is for every box in the world that has a square base and that you are paying $2 per square foot for the top and $1 for everything else. That's every square base box. But we want our box to be special. What's our box going to hold? 12 cubic feet, called the constraint equation. Constraint, I'm restricted to a box that's going to hold 12 cubic feet. All right, so let's look over here at our box. And remember, when you're looking for the volume of something that goes straight up, don't you get the area of the bottom? Multiply times the height. So what is the formula for the volume of this box? X squared h. X times h. So we'll just substitute right here. I'll just bring it down here so we can see it. X squared h equals 12. I need to find a way to get that into my formula, so I need to solve for one of these variables. Looking at that, is it which one do you see is going to be the easiest one?
4xh.
Okay, let's solve for the h and substitute it and get it already in terms of x. It's not c of x yet. I cheated a little bit. I knew I was going in the direction of x. Sorry. H is equal to 12 over x squared. Now tell me again why I got to go put this h into this formula. Well, I got to get one variable for sure, but until I restrict the volume size, this box represents any square base box where the materials cost $2 for the top and $1 for everything else. So I need to come in and replace the h. I could have replaced the x, but I think it would have been a little harder to do that. All right, so we have the cost function. C of x equals, well, I'm going to go ahead and add 2x squared plus 1x squared and get what? 3x squared plus 4x times 12 over x squared. 3x squared, what's the rest? Plus 48 over x. Okay. All right. What have I just found? The cost function for my box. For this box that I'm going to purchase that make that has a volume of 12 square feet. So I could pick x to be 1. Right? I could pick x to be 1, come back and solve for h, and I could get my cost for what it's going to be. But that may not be the most efficient cost. All right, I'm looking for what minimizes the cost function because I want to spend the least amount of money. What are you going to do now? You want to minimize this. What are you going to do? Take the derivative, set it equals 0, or look where it's undefined. By the way, x, here's my original function. What's the domain here? Okay, well, first of all, since this is a box, we know we got to be 0 or bigger. And if it's a box, x couldn't be 0 anyway, or you wouldn't have a box, correct? So my domain is x has to be greater than 0. All right, so take the derivative, and let's find what minimizes the cost. What values for x minimize the cost? Okay, I rewrote 48 over x as 48x to the negative 1 so I could quickly take the derivative. So the derivative of 3x squared is 6x. Then I have minus 48x to the negative 2, which is minus 48 over x squared. Everybody good there? All right, now, what am I going to do with this? Set it equal to 0. All right, now, this is a rational equation, and because x can never be equal to 0, I'm going to multiply through by the common denominator to get rid of fractions. Why can't x be 0? It's a box. That's one of the dimensions. Okay, so there's no way my denominator can ever be 0. So I'm going to do that little golden rule, multiply all the way through, both sides by the same, do unto one side of the equation as you do unto the other. Okay. Multiply through by x squared, both sides of the equation. This is just one way to solve it algebraically. All right, so when I multiply through by x squared, what is my first term going to be? 6x cubed. Now what? Minus 48 equals 0. I could only do that because x couldn't possibly be 0. Otherwise, I'd be multiplying through by 0. All right, so let's just solve this. 6x cubed equals 48. X cubed equals, what, 8? Divide both sides by 6. So x is equal to 2. Okay? Now, we're just going to trust that this is going to be a minimum because I'm looking at the time. But how would you verify that it's a minimum? Okay, I'd have to pick a number bigger than 0. So I might pick a 1 and put it in the derivative. Well, let's do it while we're at it. If I pick a 1 and put in the derivative, is this negative or positive? Negative. So the function decreases. If I pick a number bigger than 2, such as 1,000, what's that going to be? 6,000 minus a real small number, positive. So it's going to go from decreasing to increasing. So at x equal to 2, you're going to have your minimum. All right. So when x is 2, that is the minimum, and you're looking for the dimensions. If I know x is 2, how are you going to find out what h is? Just go right here, right? We have that h is 12 over x squared. So we have 12 over 2 squared, which is 4. So it's going to be 3. So our box will be a 2 by 2 by 3 foot box. And if you wanted to know what that minimum cost was, you could use your cost function and put it in there. And just to prove it to yourself, you could go back to this cost function and put in x at 1, x at 10, x at 3, whatever, and actually get what the cost is. And then go back and put x at 2, and you'll see that you'll have a smaller cost function. Okay? All right, so when you're running a business, you want to be efficient. You don't want to just go, oh, let's just get a box that's a 1 by 1 by whatever to come up with a 12. I guess that would be a 1 by 1 by 12. You know, that's not efficient use of your money. All right, everybody good? Don't you love derivatives for helping you with this? All right, the next thing we're going to do is look at the inventory type problems. Inventory. All right, this is, you're running a business. I'm just going to give you a little general overview and then we'll go to the problems. Inventory. You're running a business, and let's pretend that every year you know you're going to sell 100 TVs. In the year, you're going to sell 100 TVs. Okay, so the question you have to decide is, and by the way, this is theory in that you have to assume that you sell the same amount of TVs every single day, so it's going to be a linear assumption. All right, so you're not going to assume that right at Christmas everybody buys a bunch of TVs. That throughout the year they're evenly spaced. All right, so you might say, okay, should I buy all 100 TVs first day of January and store them, and then over the course of the year, by the time I get to December 31st, they're all gone. And then the next year, I would buy another 100, and they'd be gone. Okay, or would I be better off for storage purposes, insurance, all that good stuff, to buy 50 in January, let them run out June 30th, buy another 50, they run out December 31st, and then you start your whole year again? Or should I buy 10 every, that's hard for me to figure. Okay, buy 25 every 3 months, right? 25 every 3 months. What is going to cut down on my inventory cost? All right, let me just show you a couple pictures in the book so you don't think that I just pulled this out of, right, made it up. All right, I'm on page 189. It's talking about inventory control. When a firm regularly orders and stores supplies for later use or resale, they have to decide the size of each order. And a lot of times you have what is called carrying cost. This is your insurance, your storage, cost of capital that's tied up in the inventory. Like you've already paid for it up front. You could add your money sitting in an account or in some interest. The other is also called ordering cost. Every time you order, they're going to charge you a little fee for shipping, processing. Seems like those fees just get bigger and bigger every time I order something now. Have y'all started noticing that? They'll send you something that's $20, but they charged you $18 in shipping. Okay, All right, so that's how they make a little money there, I think. All right, so you also have what are called ordering costs. Now, the first example, which I'm not going to exactly do in the book here, but what they're trying to do is to get you actually put in 1 order per year, 2 orders per year. See, I said all 100 TVs the first time, order 50 at a time, or order 25 at a time. This is a different problem, but it's the same concept. All right, then we flip the page, and they drew a picture just like I did, where you order all at once, you order twice a year, or you might order 4 times a year. Okay, now the other little thing that I didn't point out to you, sometimes when you are looking at the cost of insurance, they're going to charge you insurance based on the average inventory level. The average inventory level. Because if you were ordering all 100 at one time, and by the end of June, you should be down to 50, wouldn't you hate to be paying insurance on less than 50 after that? I mean, because you'd be paying insurance on 100 all the way through the year. So a lot of times insurance will charge you based on the average number that you have in storage at any one time. So in this particular problem, looks like they were ordering 1,200, so the average number you'd have in storage is half that, 600. Or if you did 600, the average number is 300. Okay, and you would just be paying insurance on the average number of your order, which is half of your order. Okay, so this particular problem had you actually figure out the inventory costs based on different sizes. We're going to just jump up right into the problem and say, okay, well, we want to know how many should we order. All right, and the problem I have picked is first number 4. Number 4. And we're on page 196. All right, be sure you work the problems in the book so you'll have more examples. Okay, problem number 4. We have a furniture, this is page 196. A furniture store expects to sell 640 sofas at a steady rate next year. Okay, they expect to sell 640 sofas, and just consistently they're going to be sold out of the store. I mean, that's the only way you can figure these. All right, the manager plans to order these sofas by placing several orders of the same size. Some books will call that lot, L-O-T size, lot size. Okay. Placing several orders of the same size spaced equally throughout the year. So are they going to order 320 sofas twice a year, which means January and June 30th? Or are they going to order them 3 or 4 times a year, whatever? All right, so the key thing is several orders the same size equally spaced throughout the year. Well, there's a cost to order. Ordering cost for each delivery is $160. So every time you place an order, they're going to charge you $160. Carrying cost, this is your insurance, building, lack of capital, and all this stuff. It's based on the average number of sofas in inventory, amount to $32 per year for 1 sofa. Now, this particular problem never told us what the price of the sofas are. So that didn't come into play. Some of your problems will say, and the sofas cost so much per sofa. But we're going to be looking for just minimizing the inventory costs. Coming into play is not the price of the sofas. Okay, so we're just ordering. All right, then it tells you all this stuff which I'm about to tell you. All right, ready to go, everybody? Got the problem? Oh, by the way, they call it economic order. Economic order means how many sofas should I buy at one time and how many orders per year so that I'm actually minimizing my inventory cost. That's called economic order. Okay, how many times per year and what lot, L-O-T size. Alrighty, so here we go. These are called inventory problems. You usually have one of these on your test. You usually have one of each of these kind of problems on your test. Inventory. Okay, the first thing we know is that we're going to buy 640 sofas this year. All right, so we're going to let X, and then your book encourages you to do this, X to be the I don't think this book is calling it this. Lot size, which means the number of sofas ordered each time. Okay, and then we use R to represent the number of orders per year. Okay, so you tell me what X times R is equal to. The lot size times the numbers of orders per year should equal 640, right? All right, this is my constraint. Okay? All right, that's my constraint equation. Because I've decided I'm going to purchase 640 sofas. All right, just a little visual on this. In January, I could order 640 one time, store them, and by December 31st, they're all gone. I could order twice a year at 320, reorder June 30th, another 320, and like this. Okay? Alrighty? Let's go back to the problem and see if we can come up with what it is we're trying to minimize. What are we trying to minimize here? What function are we minimizing? That minimizes what? Inventory costs. Go to the part of the question. We want to minimize inventory cost. That's all we're worried about in this problem. Okay, so the kind of function we have to come up with is inventory cost. This is inventory. Oops. Inventory cost. Okay. All right, so let's see what goes into the inventory cost. The ordering cost for each delivery, the ordering cost, every time you order, it's going to cost me $160. If I ordered once that year, it's $160. If I order twice that year, it's going to cost me $320. What are my symbols going to be that represents that? Yes, it's going to be 160R. 160R, because R represents the number of orders per year. And you can always say, okay, if I did it once, if R is 1, that's 160. If R is 2, it's going to be 320. If it's R orders, it's going to be 160R. Okay? Everybody good? All right, let's see what other costs come into the inventory. Carrying cost. So we got ordering cost, and now we have carrying costs. That's based on the average number of sofas in inventory. That is going to be $32 per year for one sofa. But it's based on the average. All right, let's get this average straight. If I ordered 640, what would my average be? 320 is my average in inventory. This is the average. If I ordered 320, what would be my average in inventory? Thank you, 160. I couldn't do that in my head. All right, if I order X, what is my average in inventory? 1/2 X. X over 2 equals average number in inventory. Okay, average size in inventory. Everybody got it? Okay, so it says it amounts to $32 per year for one sofa, and we're going to base this on the average number in inventory. So how do I determine the carrying cost? Okay, it's going to be $32 times the average number I have in inventory, which is what?
160?
Yes. 32 times X over 2. That's $32 for one. I have X over 2 in inventory. Does that make sense, everybody? So that's the ordering and that's the carrying. All right, what's wrong with my equation here? I need to minimize this cost. What's the problem? Concern. I got too many variables, and this represents the cost of no matter how many sofas you order, right? All right, so we need to find a way to get in this important little detail right here that we're going to have 640 sofas during the year. All right, it doesn't matter which one I solve for. Yeah, let's just pick R. R is 640 over X. That's how I get the 640 into my problem, because the way the cost is so far, it didn't matter how many I ordered at a time or how many reorders, okay? All right, so my new cost function will be 160 times 640 over X plus, and let's go ahead and simplify this. What's that, 16X? Okay. All right, that is the cost function. Now, what am I supposed to do to this? Am I solving the cost function for X? What does the problem say I need to do to this cost function? Minimize the inventory cost. This is the cost function. How do I find the minimum? Take the derivative, set it equal to 0, and solve, right? So once you got your cost function, you're not done. That represents the cost for no matter how many you order at a time, right? You might say, I'm going to order 10 at a time. That would be the cost. I might order 30 at a time. That would be the cost. I might order 100 at a time. That will be the cost. Of course, it's got to be divisible by 640, whatever. Those will be costs. I want to find out what value of X minimizes that cost. So you're going to have to take the derivative, set it equal to 0, and we have to quit here because we're 1 minute past our time. Have a great day, everybody. We'll pick up here.